W1VLF.
Hey everybody, my name is Paul, W1VLF, and welcome back to the lab. Today's discussion and overview is going to be about some more optical DX. And if you follow this channel at all, or are on the microwave groups, you know that I've been experimenting with daytime optical communications. In this case, I have two transmitters. I will show them to you, and we'll get a closer look later. Here is the 120 LED transmitter. Each LED there is a Vishay 5940. They run at 940 nanometers, so they are invisible to the eye. And here's the other transmitter, and we'll get a much closer look at this. This is a single LED right here, one of those Vishay 5940s, and it's being driven by a GPS module here that gives timing for Q65 and CW and carrier and all that. So we'll get a much closer look at that. But I want to give a shout out to Renee V2UG, who has been indispensable in getting some code written for this microprocessor here, or microcontroller, to get Q65, actually getting the library and the tones and everything in there and making it actually work. And also there's a GPS module, and he's taken the output of that module, locked it up so that you're on real time, and you start transmitting Q65 at the proper time, right at the very beginning of a minute. So that's how this gets its time information to be correct, sub-fractions of a second, milliseconds, plus or minus. And we'll give a much closer look at that too. And the other group is N0AN, K5GZR, and all those guys that are on a Zoom group meeting that we have almost every day. And those guys really kind of help me get to understand Q65 and see its advantages. And certainly you're going to see some of the advantages here when I show you the playback. I made a IQ recording yesterday, 500 meg big, of these two transmitters. Now again, on this transmitter is just CW and carrier only. Okay, it runs at 14.4 kilohertz. And the reason why it runs at 14.4 kilohertz is because of the TTL clock that I used. I wanted a crystal controlled frequency, so that when I looked at frequency X, 14.4 in this case, I wanted to know if I was looking in a narrow window on an SDR that my signal was going to be there. So it had to be crystal controlled. And then when you divide it down, one of the frequencies conveniently came out at 14.4, and for some reason 14.440. That seems familiar to me for some reason. But anyway, that's what this does. So there is a TTL oscillator in here, and a divider to get it down to 14.4. Then there is a 12 volt. The power supply is 12 volts, comes from a battery, and I got a little ammeter on the back. So this thing pulls about 2.5 amps on peaks with 12.8 volts. Not peaks, average, so the peak is much higher. So this one is just CW and a carrier. This one is single LED. And the time, I'll give you the time. The time on this is at the top of the minute. This sends Q65 30 mode A for 30 seconds. Then it sends W1VLF FN31LS, and then the rest of the time period is again just a CW carrier, so that's for aiding in alignment and whatnot. So let me change the camera, and we'll take a closer look at these and see what you can see. Okay, I hope you guys can see this decent. This LED is plus or minus 3 degrees at the half power beam width. So at 6 degrees wide, you're at 3 dB down, or half of the power that this LED emits. And so what do we have on here? Well, I try to run a standard connector with, so everything's at 12 volts. I don't have to worry about polarity or any of that baloney. So whenever I have this connector anywhere, it's going to be 12 volts plus in the middle. So the first thing we have is a converter that down converts to 5 volts. It's one of those little buck converters, regulates to 5, and it drives the ESP8266 here. And this microcontroller is available everywhere. It can lock to, I can use Wi-Fi, or in this case I'm using GPS. And again, V2UG is the gentleman, Renee, we spent time on Zoom, who wrote up in this software. What it does is it waits until this GPS module is locked, and here's the antenna for that. And that, by the way, works indoors just as well as outdoors, and it's very fast to acquire the time. There's a 1 pulse per second that comes out of this device, and the microcontroller spits out a 5 volt square wave at 17.325 kilohertz, which is the fundamental frequency, and then the tones for FTA are added to that. That drives a power FET here, which is it's a logic level power FET, so no problem driving that. And that's in series with the LED, so I can control the current with this resistor into that LED. And again, having this scope on here really makes a difference, because you can't really eyeball it. And especially in my situation where there's no one on the other end of the circuit, I have to, set equipment up, I have to point it in the proper direction, and then I have to drive to the other end. So just to give you a quick heads up on this, this is one LED. The other transmitter is, hold on. All right, this one is transmitter number 2. Again, this is the one with the 140 LEDs. If you count 1, 2, 3, 4, 5, 6, 7 LEDs are in series, and then there's 20 parallel rows here and 20 parallel rows here. And in series with each one of these 7 strings is a 10 ohm resistor. So these are essentially 40 rows of 7 in parallel. 3D printed template. The LEDs are pressed in, and then a drop of super glue is on the back side to hold them all in place. This one also has a scope on it. But if you do the math, from 1 LED to 10 LEDs would be a 10 dB difference. From 10 to 100 LEDs would be a 20 dB difference. So this is 140. And why 140 diodes? Because it just fit nicely in this box. There's a fan here that sucks air across all the wiring that's inside. And there's another fan here that blows. This is your suck and this is your blow. Anyway, this one pressurizes it, and this one draws the air out. And after about a half hour or so of running, if you feel the LEDs in the front, you can tell that they're warm, but not hot, not by any means hot, even on a warm day or down here in the basement running from 12 volts. I'll fire it up real quick. 12 volt battery. Just a gel cell, nothing special about it. But I'm going to fire it up, and let me make sure I have it right. Okay. You can hear the fans come on. And then in the back of this, there's a current meter. And you can see that it's just sending CW right now. Peaks about 2.5 amps if you look at it with a digital meter. But that's with a square wave, so half of the time it's off, half of the time it's on, and yeah, there's about 2 amps. My battery's a little bit low right now. But anyway, that's this transmitter. Now, if I took the back off, which I really don't... Let's see, can you see it? I can't see what I'm doing here, so I don't know if you can see the LEDs here. Maybe you can with it this close to the camera. But in the back of this unit, all those LEDs, the wires stick out, okay? I didn't clip any of the wires because that's where the heat goes, through the metal. So those fans are blowing directly across that. Another thing I wanted to show real quick was these are called, what is it, a GPS mouse. That's all it is, basically. It's got a GPS receiver in there and some sort of converter so that it can talk to USB. And then the USB in the computer, you run a program called BTK Time, I think it is. I'm not 100% sure. It's just over. I just use it all the time, and I don't know. I think I call that out in some of the live on the field footage. Anyhow, this will get you within a minute or so. Get your computer locked again to fractional, to milliseconds. Very easy to do, and you need that for when you're in the field with Q65. Anyway, I just thought I'd show that real quick. These are about $6, $6 or $7, shipping included on eBay. It's unbelievable. Here's the receiver. This is an AirSpy Discovery. These have gotten a lot more expensive. They're probably $120, but this is a general purpose and a really good receiver for LF, VLF, all the way obviously down to VLF because I'm using it at 14 kilohertz. And I run SDR console with that. And the reason why I'm using an SDR and I'm not using a 1 kilohertz tone or 800, let's say you could build this whole thing running it at 800 cycles or 500 hertz so that you could hear it in your ear, is because this gives me a lot of handles, a lot of easy ways, that I can change bandwidth, I can change sensitivities, and it's also an interface using SDR Console 3 that I'm very, very familiar with. So it's just so easy. USB, very small receiver, and then I use a whatever this is, 316 or 174 SMA from the actual optical receiver. And we're going to take a look at that optical receiver right now, and I'll show you what that's made from. Now for the optical receiver. I guess first off, this is a delta lens, right? This is an old projection television lens. The input, if you will, the input lens is about, or the objective is about 5 1/4 inches, roughly, something like that. I just basically strap it right to a piece of channel aluminum here, and then to the tripod mount. But the real meat of the program, the thing that really helps out a lot here is this. I'll tell you what, let me just disassemble this so I can show it to you up close. So here's the back of the lens. It's adjustable. You can slide this piece in and out if you like to get your focal point. My way to mount it, very simple, just using 2 of the mounting bolts with 1/4 rods coming out of it, and then the receiver slides on, and by changing this adjustment, I should have done that, by changing this these screws here evenly, you can move the detector into the focal point, which is about 1.5 inches, I think, back. Maybe it's 2 inches back from the back plate here. Actually, you should go by the back of the lens. Anyhow, and easy to mount, right? You just throw a clamp around here, hose clamp, and a piece of channel iron, and that self-centers everything, so it's very, very easy to mount. I'll show you the receiver now. So here's the actual receiver, and what we have here is a 1/2 inch by 1/2 inch, actually you buy it in millimeters, and that reflective surface is a 940 nanometer bandpass filter, very narrow bandpass filter. When you're working with daytime outdoor light, you need to have a front end filter, because the detector, which is on the back side of this, has an integral filter, but not as sharp and narrow as this, and so this helps an awful lot. Also, what you don't want to have is a lot of light scattering all around the surface here. You know, ambient light scattering and getting into the sides of the detector. And one of the more important things is, if you think about this, this is a tiny little solar panel. If you put it out in sunlight, you're going to get a DC pulse out of it. Now I get 1.5 volts out of this, no current really, right? But you get about 1.5 volts out of this in the sunlight, and that 1.5 volts is going right into your amplifier's front end. So there's a DC blocking capacitor here of about 0.1. So this is just for scattering. That's the bandpass filter, the DC blocking capacitor. And now we'll talk about, this is probably one of the more important pieces, and this is the transimpedance amplifier. I go through a small piece of coax to the transimpedance amplifier, and then the output of it drives the SDR. I chose this because it's a relatively quiet amplifier in terms of noise. I also chose it because there's 3 adjustments in here for the feedback resistor in the transimpedance amplifier. So this can get extremely sensitive depending on, I think there's 3 different amplifier settings here, feedback, right? So there's a 1 meg, a 10 meg, and a 1 gig. Excuse me, maybe it's a 10 meg, 100 meg, and a 1 gig. But for any kind of daylight work, you have to use the lowest feedback resistor, which gives the widest bandwidth, and you know, as you go higher in feedback resistor, the bandwidth rolls off, and the noise and sensitivity gets better, and blah, 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 blah. Anyway, so that was part of one of the reasons why I bought this. The other reason why is it's cheap as hell. It's like 15 bucks back before everything started changing. Runs on a single supply, 4.5 volts. I've actually left this on for a week because it only draws a couple of mils, and it's still been running. But this is the key thing to really get your sensitivity up. That and the bandpass filter up ahead of this, and the integral bandpass filter here. Now I do have another receiver that uses an avalanche photodiode, which is completely all built into one, and I had to definitely put a bandpass filter in front of that because it was just wide open. Anyhow, that's the receiver. Let me slap that back together again, and then we'll go over to the computer and look at some of the actual footage of what I was doing in the field. Whoop. So here we are. What is it, March 13th or so? And if you can see that blue on the horizon here, that's as much as I get. That blue horizon, that blue looks like trailer or something right there. And those hills above that are where there is a spot on Johnny Cake Mountain in Burlington. I'm in New Hartford right now, on top of, what is it? Cotton Hill, and there's a whole bunch of different sites that I could do from here, but this is a 4-mile path, so it's an attempt. This particular transmitter here is sending out Q65 for 30 seconds. It has a GPS module, antenna module, and then a microprocessor that sends out Q65 for the first 30 seconds, W1 VLF from FN31 for the second 10 seconds or so, and then a carrier the rest of the time. This is that one LED transmitter. Let me squeeze this back down. This is that one LED transmitter. There it is right there. Okay, rifle scope to line it up. Ooh, this is not good. And here is the big array. I doubt you can even see this, but oh yeah, you can see them. It's hard to stay on axis with all of these at the same time. Some of these, you have to have the camera just right, but they're all on. Cooling fan on the bottom and the top, drawing air through. It's a peak current there of about 2.5 amps at 13 volts. All right, so here's the horizon again. So lots of good spots up here, at least when the trees are, no leaves on the trees. And that's it. I'm headed to the other end. Okay, folks, now we are in Burlington on Johnny Cake Mountain Road. And I'll zoom in. If you see that pine tree to the right and the deciduous tree to the left, that's 4 miles from the location that I'm located at right now, where I'm located. And in the very center of that picture is a couple of pine trees. Those are right in back of the transmitter site. I've got the receiver, 5 volts, 5 point something, powering the what do you call it there? The trans impedance amp. It's hard to see in there, but that shiny thing is a 940 nanometer filter. And here is the lens. That's what it looks like. Okay. So now we are transmitting on 2 frequencies. The large transmitter with the 120 or 140 LEDs is on 14.4 kilohertz, and the reason that frequency is chosen is because it was some TTL clock frequency that was divisible by a number. It's a clock running at some frequency and then divided by 2, divided by 2, divided by 3, divided by 4, 5, 6, 7, 8, 9, 10, like that. And so 14.4 is where that comes out, crystal based. The other one is on 17.3. Oh, look at this. We'll zoom in. What is that called? The hunter's moon or the blue moon or some moon. Anyway, we're here for more important stuff. You're looking at the screen here, and you're going to see, let me zero this down. Here's the screen. There is the 140 array, and that is the single LED. One LED at 4 miles, sending Q65. Now it's going through. Okay, 100. All right, there. Now it's a carrier. And again, I'm making a recording of these, an IQ recording, so I'll be able to look at this more critically when I get home. But it looks like it's I don't know. Let's see. 10, 20, 30 plus dB stronger. And now let's flip over to the Q65 screen. Here's what the Q65 signal looks like. Okay, what happened? I must have hit something. Yeah, I went off frequency. Let me go back in my memories. 17.325. Okay, now we'll go back to the screen. Okay, so here's Q65. Those are the ones we captured so far. So at 4 miles, running Q65 with a single LED, we have a -5 received signal strength. Okay, and okay, so you'll see it's It's actually easily, very, very easily distinguished by ear. It's not nighttime yet, but it's not really daytime either. What time is it? It's like 6:59 now. So, but there, take a look at that. So I've received with this setup under lab testing, you know, from my range with attenuators. You know, attenuator is an old t-shirt. You throw it over the receiver, down to minus 25. So there is still 20 plus dB of headroom in this signal. Now, I want to say something here. I don't have I'm not at the transmit site. I want to say that I want to give a big shout out to VE2UG Renee, because he's the one who actually wrote the software for the or assembled the software to get the Q65 beacon code running, and also suggested the GPS. So I'm really excited about this. I don't know about you guys, but that is, let's see, now we're down to a -2. Really exciting. One more shot at where well, I'll do it from the back here so you can see. We're just like poking a hole right through a little gap. Okay. Bring my DSLR up here. Okay, right through that pine tree and the deciduous tree. Right there on that hill is 4 miles away. All right, enough yapping. I'm gonna stick this all together and throw it up in a YouTube video for Renee and John and Fred. So one more time, I guess let's go back to just the receiver. Actually, let me try something here. Let's go using console, go to the view mode, signal history. Okay, as you look down here, you can see that the noise is at -90 because there's still some noise in the amplifier in the back of the receiver. And the peak is at -67, 63. Oh, there's QSB on the signal. I imagine over 4 miles there would be. So -63, let's just remember that. And then what I'm going to do is I'm going to move this down. I'm going to move over to this signal, put it right in the middle of the passband. That's the multiple transmitter, the multiple diode transmitter. So what's that, 65 to 41, 63 to 41. So it's a little better than 20 dB. I wonder if this one might have a little bit less QSB on it. It's such a high pitch because I'm using USB upper sideband, so I can copy the, so I can copy the Q65. So this, I would say, is a successful experiment. Okay, see that? Drop down to -90. So this thing is like 50 dB out of the noise. Anyhow, I'm really excited about all this. If you can't tell, right? But now I have to run back to the to that site and grab my where'd it go? And grab my transmitters before somebody comes by and steals them. One other thing I could put in here is I can make another half a mile if I go up on top of that hill, but I really didn't want to do that, you know, with people being around and whatnot. But 4 miles. Am I pumped or what? The W1 VLF 73. Back again, showing the LEDs. It's getting dark now, so you can actually see the camera has opened its iris. And let's see, can you see this one? Yeah, there it is. So that's the small transmitter, the one LED guy. And I'll back away about 50 feet or so. There we go. Okay, folks, we're in front of the laptop, excuse me, the lab computer, the ham radio computer. And as you can see, let me get rid of this clock. I was using this clock to synchronize the time so that I could get playback of the Q65. Because when you make a recording of Q65, you have to get the clock back, right? So everything lands on the minute. Anyway, this is just so that you guys can hear this. This is the 120 diode array, 140 diode array, excuse me. Okay, so now we'll go over, here's the FT8 array, or the FT8 single diode. I'm using narrow bandwidth. So you can see above the noise floor here. Let's stretch this a little bit. Okay, let's say the noise is at minus, what is this, 88 here or something. And that's peaking up here at minus 66, 68. There's a lot of headroom there. A lot of headroom. And what we'll do here is we'll go into the view mode and look at the signal history. Bring that over on this side. Oh yeah, there's definitely QSB on there. Let me fix that a little bit. Okay, that's the single LED, and we're going to switch over now. Where is it? 14.4. We're going to switch over to, well, we'll wait till the carrier comes up. That'll give us something to look at, compare. Okay, here's a straight carrier, and now I'm tuned to 14.4, which is 140 diodes. Minus 65 here on the carrier, and minus 40 or so, 44, something like that. So I will mute this, and then I want to look at one more thing, and that here's a picture of the decodes that I made, and you can see minus 4, minus 3, 0, 1, 2, 3, and then at the end here, minus 29. I don't think that's real. I was disconnecting things. It may have gotten only half a sequence. But as it got darker, you could see that the signal to noise ratio was going up a little bit. So anyhow, that's the end of this. Any questions, leave them in the comments. I think on the 22nd of March, I'm going to be at the news group meeting showing some of this equipment and maybe taking questions and whatnot. So see you guys there. This is W1VLF from the Optical DX HQ saying 73.